Alright, sup dudes, here's what we're going to do. We're going to cover some triangles, and I think these triangles are really important. I always see these kinds of problems on different various tests, and so let me just show you them. There's this thing right here, and it's, you know what, I need to make sure that all fingerprint oil is off of this thing, because that's what's causing these markers to kind of get off junk. There we go. A little bit better. It's too high. There we go. All right. Here's a very pretty standard triangle right here. This is called an equilateral triangle. It's called an equilateral triangle, and I know I didn't draw it nicely, but whatever. It's called an equilateral triangle. I usually kind of put little notches right here so that I can know that they're all the same size. What are some properties about the equilateral triangle? Do you know the angle that's inside of this thing? What are those angles?
90 degrees.
They're not 90 degrees. If they were 90 degrees, it would look like this. In fact, if more than one of those were 90 degrees, you wouldn't be able to have a triangle at all. 180 divided by 3. What's 180 divided by 3? 60. Perfect. There's 60, 60, 60 triangle. All the angles inside of the middle are the same. All of the sides are the same. I like how you said 180 divided by 3, because that actually kind of tells me that you understand. If I add up all of the angles inside of a triangle, what number will I get? 180. Perfect. You understand that. Good. This is an equilateral triangle. Is there anything else to be said about it? No. All right. An equilateral triangle is actually a very special version of this triangle right here, and it starts with an eye. Can you guys think of what it is? I'll draw this symbol like that. It's not a face, although it does kind of look like a helmet. This is an isosceles triangle. Perfect. Do you guys remember some properties about the isosceles triangle? Or however you spell it. Yeah, exactly. All right. An isosceles triangle has two sides that are the same. Is an equilateral triangle also an isosceles triangle? That's my question to you. Yes or no? Yes, it is. Because does an equilateral triangle have at least two sides that are the same?
Yes.
Yes. It just so happens to have a very special version where the third side is the same, so technically an equilateral triangle is also a version of an isosceles triangle, just like a square is really a very special version of a rectangle. Does that make sense? Because a rectangle is defined by having all 90 degrees inside of it. And, you know, I mean, a square has all 90 degrees inside of it. It just happens to have all the sides being the same size as opposed to, you know, whatever. So we have our isosceles triangle. I can tell you for sure that this angle over here is the same as that angle over there. What is that angle? I can't tell you. It depends on the size of these things. The longer these sides, the bigger this angle is going to be, but I can't tell you exactly what it is. All I can tell you is that the opposite angles of the equal sides, so like this side angle and that angle right there, they're going to be the same measurement as each other. Does that make sense? All right. Here's another one. It's a very general one. This is just a regular right triangle. I usually label this A, B, and C, and since this is a right angle, I put a little square right there, because square kind of makes me think right angle. Is there an equation that you know that relates A, B, and C sides of a right triangle? Made by a famous Greek dude. There we go. Awesome. A squared plus B squared equals C squared. You've heard of that before at least, right? The hippopotamus theorem. That's a hypotenuse, but the Pythagoras theorem. Yes, the Pythagorean theorem, that's what it is. Made by my friend Pythagorean. I think it was around 400s. He made this, and he's a pretty awesome dude. He liked gyros and philosophizing, baths, that kind of stuff. I know him. We were good friends, schoolmates. Yeah. Alright, so a squared plus b squared equals c squared. The a, the b, if I square both of them, that's equal to c. Hey, can't I take the square root of both sides and just make this a plus b equals c? I
don't think so.
No, I don't think so. I mean, shoot, if that were that easy, why didn't he write it in the easier version? Why would he write the harder version if he wrote it this way? No, you have to square a, and you have to add b squared, and then equal to c. If you wanted to square root both sides, you would get this. You would get c is equal to the square root of a squared plus b squared. And there's no way to simplify that, really. Got it? So, that's the Pythagorean theorem. It's actually really important. There is a special version of this right triangle, and what it is we call these Pythagorean triples. One of the most famous ones that I guarantee you, you're going to see this thing happen so much in the next lecture, in the next couple of lectures, that you're going to be like, man, I can't believe that this triangle popped its ugly head up. It's called a 3-4-5 triangle. And it states this. If this length is 3, that length is 4, then I can tell you what that length is. 5. Because 3, 4, 5 happen to satisfy the Pythagorean triple a squared plus b squared equals c squared. Because 3 squared plus 4 squared equals 5 squared. Because 9 plus 16 is 25. 9 plus 16, do it in your head. What is it?
25.
25, yeah, all right, cool. That is a special triangle. You will see this triangle pop up its ugly head, guaranteed, all the time. I promise you, at least twice on any test you take. And it's devious. You won't even see it, like, you won't even initially recognize it off the bat. All right? Is there such thing as a 4, 5, 6 triangle? If this were 4 and this were 5, is this 6? No. No, there is no such thing as a 4, 5, 6 triangle. I'm telling you these Pythagorean triples because all we did to figure out the Pythagorean triples is we plugged in A and we plugged in B, and then we figure out what C is, and we said, hey, those are nice numbers that go nicely together. You have to memorize 3, 4, 5. Now, you might not see 3, 4, 5 exactly as 3, 4, 5. You might see it as 6, 10. What is this length right here? Nope, 8.
Okay.
Why 8?
Because 4 plus 4 is 8.
This is really a 3, 4, 5 triangle as well. I don't like how you said 4 plus 4.
4 times 2.
Yeah, 4 times 2. I'd rather you say 4 times 2, even though you're thinking, hey, wait, that's the same thing. It's because you can multiply all of these things by 2, and this is really just a 3, 4, 5 triangle in disguise. I mean, essentially, imagine if this were like Adobe Illustrator or Paint or whatever, and I have a triangle here, and I just grab the right-hand side and I hold down the Shift key, and then I move this thing to scale it up. That's all I'm doing. I'm just scaling the different triangle. It's not making it a different triangle, it's just making it a bigger triangle. Does that make sense?
Yeah.
So I could have multiples of this thing right here, and that would totally work. Like, for example, if this were 15, 12, what's that angle right there? Or what's that length right there?
20?
Nope.
No.
9.
Oh.
Because I just took my 3, 4, 5 triangle and multiplied it by 3.
Oh.
So this really is a 3, 4, 5 triangle. It just might not be initially, like immediately, boom, I see the 3, 4, 5 triangle. Does that make sense? And I told you, so remember I told you it's going to be hidden sometimes. It's going to rear its ugly head. This is where we're going to see these kinds of things. This is still a 3, 4, 5 triangle. I'm not going to teach it to you as a different triangle. it just happens to have different numbers. All I'm doing here is this is a regular 3, 4, 5 triangle. I'm just multiplying everything by 3. I could as well have this. I don't know, something like 1.5, 2.5, 2. I just took everything and divided it by 2. I can't, however, have my regular 3, 4, 5 triangle and add 4 to everything. You can't just add these lengths and have that work. That's why I didn't like how you said 4 plus 4. You can only scale this thing up by multiplication or division, but you can't just add things or subtract things. This would make a 7, 9, 8 triangle. There's no such thing as a 7, 8, 9 triangle. Does that make sense? Okay. All right. Another very special right triangle is called a isosceles right triangle, and sometimes you see it like this. Sometimes you see it like this. Whenever you see it, if it's a right triangle, the fact that a right triangle means it's a right angle. It means it has 90 degrees in it. So you'd see it like that. If this were the case, I remember I told you that I can't tell you what the angles inside of the isosceles triangle are, but I can tell you that I know what these angles are if it's an isosceles right triangle. Because remember, and actually Alicia, if you want to chime in on this one, or if anyone of you want to chime in online, that would be great. What are these angles if that's a right angle? You're fair game too, you can jump in. You know? They're 45, exactly. Because remember, if I add up all the angles inside, this would equal 180. This is 90 right here, so 180 minus 90 is 90. So this has to add up to 90. And not only do they have to add up to 90, they have to be the same because it's an isosceles right triangle. So this side is the same as that side, so this angle is the same as that angle. So what times 2 equals 90? 45. 45 times 2 is equal to 90. That's why I have this 45. We could call this a 45, 45, 90 triangle. I've heard it called that before. It's really an isosceles triangle because 2 sides are the same, and the angle inside is 90. If this is the case, then what you're going to have here is you're going to have 1, 1, and the square root of 2 here. And what I mean by that is that if this length were 1 and this length were 1, then this would equal to the square root of 2. The square root of 2 is a number. It's 1.41 blah blah blah, something I can't remember it off the top of my head exactly, but that's pretty close to what it is. It's just some number that's a little bit bigger than 1, you know, and you can use your calculator to figure it out. Often you would see this problem something like, all right, here's the question is, where did I get the square root of 2? Do you know? Did I just pull that out of my, throw it in on the board? Yeah. If it's a right triangle, it will obey this equation. If A is 1 and B is 1, 1 squared plus 1 squared, and C, we don't know what it is. What's 1 squared? That's 1 plus 1 equals C squared. So 2 equals C squared. So C is equal to the square root of 2. Right? Because I took the square root of both sides, square root of 2. That's where we got the square root of 2. It really just comes from the A squared plus B squared equals C squared. If you don't remember the square root of 2, don't worry, because you can just use Pythagorean theorem and figure it out. Where do you see this problem? Pop its ugly head up. I often see it like if they ask you stuff like, they tell you that this is 45 degrees, they tell you that this is a right triangle, and then, I don't know, maybe they'll say this length right here is 2. What is this length right here? X. This is a little bit harder than what you would, you know what I mean? It's about where you would go. So I would probably say something like, well, if X were 1, then this length would equal the square root of 2. So, X times the square root of 2 is equal to 2. Does that make sense? Because 1 times the square root of 2 is, yeah. So if I basically if this were 1 and I want to make it equal to the hypotenuse, I would multiply by the square root of 2. This was x instead, so I multiplied by square root of 2 to make it equal to the hypotenuse. So apparently x is equal to whatever 2 divided by the square root of 2 is. Does that make sense?
Yeah.
If you don't believe me, you can plug it into the quadratic equation, or you know what? Not quadratic equation, the Pythagorean theorem. Honestly, I would actually just plug in, I would say, okay, well that's x, and I would say, all right, then x squared plus x squared equals 2. So that's 2x squared equals 2, right? I'm sorry. X squared plus x squared equals 2 squared. That's the Pythagorean theorem. I was thinking, I got this wrong. All right, so that's 4. And so I divide both sides by 2, and so I get x squared equals 2. So I'm going to have x equals to the square root of 2. Oops. Did I do something wrong here? Did I do something wrong? No. No, I didn't. This is the same thing. You're looking at me like, that's not the same thing. How can you tell?
These are the same.
No. Think of it like this. Usually in math, I'm getting into some advanced stuff. I think that part of this is, you learned this in geometry. You've learned Pythagorean theorem before, right? Part of this you learn in trigonometry, which you haven't taken yet, so maybe you haven't seen this yet. But usually what we do is we have x equals 2 over root 2, and you want to get rid of the square root inside the denominator. So I'm going to multiply this by square root of 2 on both the top and the bottom. Because if I multiply the square root of 2 times the square root of 2, that gets rid of that square root. Because what is the square root of 2 times the square root of 2? That's just 2. Does that make sense? So I have 2 times the square root of 2, that's what the top is saying, divided by 2. Because the bottom is 2. Did I lose anybody there? Alright, these 2's cancel out, and you have x is equal to square root of 2. This is saying the same thing. Alright, the last triangle I want to show you is called a 30, 60, 90 triangle. Now for a 30, 60, 90 triangle, you definitely hit this thing up a lot in trigonometry, so maybe you might not be super familiar with this thing right now. But it's basically, it's a right triangle, so it's got a right angle in there. This one would be 60 degrees, and this one would be 30 degrees. I'm going to warn you, this thing looks very similar to a 3, 4, 5 triangle. It's not a 3, 4, 5 triangle. 3, 4, 5 triangle doesn't have the angles inside as 30, 60, 90. This one has the angles where if this length were 1, then this length would be twice the size, and this length would be the square root of 3. A lot of the ideas from that come from the ideas of trigonometry, where you have sine, cosine, and tangent. And I haven't taught you sine, cosine, and tangent yet, so you don't need to worry about it. But just treat these ratios as the same as you would when we were doing the 45, 45, 90 triangle. Are we cool? So this is a 30, 60, 90 triangle. They have 3, 4, 5 triangles. They have isosceles right triangles. They have equilateral triangles, isosceles triangles, Pythagorean theorems, that kind of stuff. That's pretty much what you need to know about triangles in a nutshell, besides understanding how to get the area and the perimeter and all that kind of stuff. We cool? All right, I'll talk to you